Okay, that is the forward pass. Okay, with the purpose of forward pass, because we want to find the y1 hit and y2 hit, which is the predicted output. Once you know the y1 hit and y2 hits, then you can compute again the E1 and E2, which is the error happens there, the error or the cost function or the cost value happen at that particular points there. And then from once you compute the E1 and E2, then you can get the cost function or the total error, which is the E is equal to E1 plus E2. So now again, remember that our objective, we want to find the del E over del W or del E over del B. That is the purpose we compute this one, because that is the gradient descent step in order for you to find the optimized W and B that can provide the minimum value of cost function or the minimum error that can represent by this artificial neural network given the training data set, or in other words, to find the best fit model that can fit into your training data. Then you need to compute a gradient descent, and then in gradient descent, the objective is you want to find the gradient itself. Okay, the gradient itself. So because the gradient will determine how much you need to tune your W and your B to going towards finding the minimum cost function value or the minimum errors there. So remember that we want to compute this one, del E del W, and we want to find this one, del E and del B. If okay, here in this case we have W and B, so that's why we need to find this one or this one. So in order to find this one and this one, once you already compute the fast forward, you already know the E there. Now we need to compute the backward pass mechanism. So the backpropagation, when I said the backpropagation, is actually both step, which is forward pass, backward pass, forward pass, backward pass. So you will do this iteratively to find the optimum W and B. So now we just finished the forward pass. Now I would like to discuss about what happens to the backward pass, and again the purpose of backward pass, because you want to find this one, del E del W, del E del B. Okay, so just from this, because we have a lot of W and B, okay, of course I cannot show you all example, all thing derived from here to here. So I just take one cases there. We talk about this one first, because now it's a backward pass. When we talk about backward pass, it must start at the last layer towards to the input layer there. From the output layer towards, means that the backward pass should be into that direction. So that's why we start from this layer. Okay, but if you see in the forward pass, because there is going toward that direction, that's why we start at this layer, the input layer. So at the backward pass, from here, let's consider only one W. Okay, consider only one W, which is W35. So we want to know how much a change in W35 affect the total error. So this is again, this is why we want to find, or our objective is why we want to find the del E over del W35, is because that is represent how much a change of W35 affect this total error. So means that how much this W contribute towards this error. Okay, of course it's not just this W. You will need to find all del E del W, del E del WY35, del E del W45, del E del B5, and so on, each and every W and B over here. So what is the meaning by del E del W35 is actually is the total change that make this error happens. So or in other words, how much the contribution of this W35 towards providing or resulting this error. So that's why we need to find the del E of over the del W35. Okay. Sorry. Okay. Okay, there's a little bit wrong in this statement there. This is not also known. Okay. Just delete this part. Just delete this part in your notes. Actually, it's not also known as a. This one is actually is a updater. It's not a del E del. It's not like this. It's not similar to this one. Okay. Later you see that what is the meaning by that that delta rule. This is called a delta rule there. Or this one is actually is an updater of your W35 updater. Okay, it's a this updater of W35. So del E del 35. Okay, if you sorry. Okay, sorry about there's a wrong in your slide note there. Okay, del E del W35 is not similar to this one because this rectangle W here is represent the W35 updater. Is not del E del 35. Okay, I will explain later what is the meaning by this. Actually, is a delta rules updater. There is a updater for your week 35. Okay, this is another name for your del E del W3. Is a partial derivative of E with respect to W35. Of course, this is a partial derivative with respect to of the error functions there with respect to your W35, and this is also known as a gradient. Again, this is a gradient. The gradient with respect to W35. Of course, the gradient itself is a slope, which when you count the slope value is actually how much change. Okay, in other words, the slope is also known as a represent how much change of that point with respect to this function E there, or the cost functions there. So that's why we need to find, or why we want to find this del E over del W. Doesn't matter which W you want. Okay, and then of course, in order to derive or to find this expression, you need to know the change rules. Again, same as the previous lecture related to regarding the linear methods, where in order for you to find each and every derivative there, del E del W, you need to use the change rule to express that from the input layer value, input layer value E there, through each and every B and W that exists. Doesn't matter is it from the output layer or the hidden layers there. Okay, so this is the updater there that I mentioned before. It's not similar. Your updater should equal to alpha del E over del W35. Actually, this is the updater. Just remember that. Okay, if you remember that, because during the gradient descent, remember that I just write the updating process of your W and your B based on gradient descent. You need to find your new W should equal to your current W minus delta. I'm sorry, it's not delta, this one is updater, updater of your wake W35. Okay, so here this one is equal to alpha, which is your learning rates, and your the change with respect to the error functions there, which is also known as your gradients. So that is why they call this process there is as a gradient descent. Okay, because this one is based on the gradients, but of course it's not a totally gradient. It should be have a one variables that called alpha, which is your learning rates. Of course, if you want to make sure this updater equal to your gradient, then you can set your learning rates equal to 1. If this is equal to 1, then this one is equal to this one. But normally we will tune this one from 0 to 1, means that sometimes we don't want to have fully gradient value update your W35, because it will make your step more bigger and you cannot find the minimum, the global minimums there. That's why this one you need to have the value which is from 0 to 1, and in most of the time you will give the value which is very small, 0.0 something, so it will make the learning process slower, because the number, the distance of the step is very small to going towards the minimum value. Okay, so that is the updater. Okay, this one is the updater. The updater of your W35 is represented by this triangle W35 updater. So if this is the updater, and again this is this one, it doesn't matter. This one is you need to set by yourself the alpha learning rates. Now we want to find this one. Now because this one have been set, it one is fixed, means that it is already there, the value. In order to obtain this updater, you need to know this one. And again, that's why our main objective is we want to find this gradient, because we want to find the updater. Okay, so how do you express this one? This one, if you extend from the previous slide there, how to find that one? You can express in this way: del E over del W35 is equal to del E over del Y1 hit, then multiply with del Y hit 1 over I'm sorry, this should be net there, forget to put there, it should be del net. Okay, del net 5 and del net 5 here. Okay, this one is again this is what we call as a change rules. Okay, so in this model, artificial neural network, you will use a lot of change rule as compared to the previous one, because we have a multiple stages of neuron, or multiple stages of logistic regression, or linear regression, which is stacked together or cascade together. So that's why there's a lot of change rule to do this, as because you have, if you increase more and more neuron, you will increase more and more linear regression or logistic regression inside your network. So that's why the change rule will become longer and longer to find, or to find or to obtain this del E over del W, whatever W you want to find there. Okay, so if you go back here, okay, to find del E, okay, again we want to find at this position. Okay, this position there, del E over del W 35. So from here, this is the expression. Of course, the total errors there, you must this one plus this one. Okay, here you remember that we have here, there's a net there. This one is net 5. This one is your y05. So of course we have the activation function there. So to find del E over del W35, because E here is come from here, okay, it's come from here. Now del E must over what? What is the independence variable of E? E should be y1 head there and y2 head. If you remember, actually your E there consists of this. It's depend on two variables, which is y1 head and y2 head. Okay, because if you plus E1 and E2, this one contain y1, you can see here, and E2 contain this one. So that's why this function is depending on this one. So that's why to find this delta here, then you need to extend the change rule into del E over del y1 head. Okay, why we need to find this one over with respect to del y1 head? Because we know that our E have two independent variables, y1 head and y2 head. So now we want to process the W35, which is only involved in finding this node or this neuron, and this neuron will provide only y1 head there. Okay, however, and y2 head only produced by this part, this direction. Okay, so means that there's no relation between this W35 and y2, but there's a relation between this W35 and y1 head, because to find y1 head you need to know the W35, but to find the W2 head you don't have to know the W35, because W35 is here. W2 head is only depend on B36 and W36 and W346, which is this one. So that's why we only do a partial derivative of del E over del y1 head. Okay, that's the reason why we start our change rules like that, because when we see the pictures, to find the del E over del W35, we must start at del E, where del E is this location, because E is at this location, and you see that E is depend on two variables, which is y head 1 and y head 2. But to find the W35, you only need a W1 head, because this one to produce y1 head you only need W35, and W2 head here does not have relation with W35, because to find W2 head you only need this one and this one. Okay, I hope you can clear about that, how actually we define and how actually we start our change rule to do that. Once you know this one, then still you need to extend your change rule, of course at the numerator there, still you need to follow the denominator of the previous one. So that's why I follow del y1 head over what. So now it's over what. So and then you know that what is y is 05, and 05 is a output from the activation function f there. So this as activation function. Okay, just I just explain here. Here. So y here is come from your activation function. Okay, during the forward pass, we compute these two. One is active input function, another one is activation function. So we know that our y is depend on net, because to find y hit 1 there, you need to compute the activation function f where the input is net. So that's why then you can continue expressing this thing with del y1 hit over del net 5. So why? Because this is already there. There's a function there during our pass, forward pass. We already know this one. This is the definition of your y hit, y1 hit. Okay, so that's why you can easily find this one. Okay, so it's easy to find this one because you already have the equations there. Okay, now of course the numerator there, the numerator of another del there should be del net 5, and then the denominators there should end up with your w del w35. Okay, of course now because this one and this one is already end up together to produce your del E over del W35. Now means that now is it this one possible to obtain? Yes, it's possible, because this expression can be obtained from the input function. When you compute the input function of your net 5, this is the expression. So now if I want to have this one, which is del net 5 over del W35, I can obtain from this function. Okay, so that's why in order for you to find del E over del W35, you can express it or define it in this change rule, where you have three components there: del E del Y1 hit, del Y1 1 over del net 5 multiply with del net 3 over the del W35, and then from there you need to find one by one what is del net 5 del W35, which is this one. So this one is actually this one you derive with respect to W35, means that you will cancel this one, you will cancel this one, because it's not, it's a constant, it's not a variables. The one that consists of variable is only this component. So derivation of del net over del 35, this one become 1, so that's why you have 0,3, which is this one. Okay, so that is for this component only. How about this component? So of course this one is depends on this one. Okay, this one. So to find del y hit 1 over del net 5, then you need to know the activation function. So since we don't set yet what is our activation function, is it a sigmoid, is it a sinc function, or is it a unit step function, then we just use a variable f apostrophe to represent the derivative of our f, means that the df over the let's say this is your function f, then if I talk about del f over del x, then I just replace with the symbol f apostrophe. So that's why I use here as a apostrophe there, because that's meaning it's a derivative of this activation function over the net 5. It is same things there. Just put it first, later we, because at the end later we can set what type of activation function you want, and then once you know the activation function that you want, then you just can simply replace that notation by by do derivative of that functions. And then the third component, which is this one, del E over del Y 1 hit there. So this one is come from the definitions there. Remember that my E totals there, again my E total is equal to 1 over 2 y sorry, what is the, yep, y1 minus y1 hit square plus 1 over 2 y2 minus y2 hit square. So this is E1 and this is your E2. So if you want to compute the del E over del Y1 hit, then of course this everything here is a constant, that's why they become 0, and then you just need to do derivative of this component only. So if you compute this one, then what you get is this one. Okay, so now in order for you, again our objective, if we want to find del E over del W35, so now our del E or our del E or over our del W35 can be computed as and can be expressed as this one. Okay, so that is happened at W35. So then you need to repeat the same process to find other parameter which involve at this output layer, including the W45. It means that you need to find del E over del 45, del E over W36, del E over del W46, del E over del B6, and del E over del B5. Okay, if you repeat the same process, then and again I just put some additional notation there. You can see that this thing is also known, I just define this as a E5, which is the I considered as a local error happen in local error happen in node 5. Okay, local error in node 5. So if you talk about E5 is a local error happen at node 5. If you talk about small e6, it's a local error happen at the node 6. So I just define another notation there. I put another notation there. So don't get confused why I add more and more notation there. There's a purpose there. Later, in order for us to generalize the algorithm, we need to have if we define this, it will be beneficial if we define this notation, because later you will see the purpose is we want to generalize all the things. Okay, just added that, assume that E5 is the error happen at the error, E5 is a local error happen in node 5. Okay, which is expressed as W1 actual Y1 minus the predicted Y1. Okay, and negative value there. And I also introduce you with another notation which is also known as a local gradient or node delta, or this is also known as a delta. When I said delta 5 is a or node delta 5 is actually is a local gradient of node or neuron 5. Okay, so again it's the same expression there. Okay, same expression as this one. I just bring it at the center there, and then I define that this component is your delta 5. What is delta 5? Delta 5 is a del E over del net 5. So meaning that if you talk about something related to neuron 6, it will become delta 6. Okay, this one I want to generalize the some things there. That's why I introduced you with two notation there. One is E there, another one is delta. Okay, delta. So if in this case, delta 5 is defined as del E over del net 5. So if I try to generalize there, if you talk about neuron 6, the delta 6 is represent a delta inside the neuron 6, which is defined as a del E over del net 6. Okay, you just need to remember this is just additional notation in order for us to generalize this or to make this mechanism generalized later. So that's why I need to use this term. Just remember that if del E over del net is defined as delta, then del E over del net 5 is delta 5. Okay, that is just assume that, because this is in some textbook they call it as a local gradient, means that the gradient happen inside the network. Okay, if this is a delta 5, okay, this is the gradient happen inside the network before you, of course, the error that happened there, this is E5, sorry, this is E5, and then E5 will produce the delta 5 there, and then it will going towards propagate the error towards the back during the backward pass. It will propagate the error to direction from output layer to the input layer. That is it. Okay, so again, if okay, so del 5 delta 5 again is equal to del E over del net 5. So this is the component. So if I want to express again what is del 5 in this way, then is equal to, okay, you can see that now, because I already defined this one as our E5, or the local error happen in node 5 as E5, and then now the delta 5 is actually a gradient, local gradient happen in node 5, which defined as a del E over del net 5. So to find your delta 5 is equal to your f derivative of your activation function multiply with E5 over here. So again, if I can simplify the expressions there in order for you to find sorry, this one should be again there's a alpha there, I forget to put there. This is alpha there, and then it should be alpha time delta 5 time O3. So in other words, to find the updater of W35, then you can just simply multiply between your learning rates with your delta 5, where delta 5 is defined as del E over del net 5, time DO3, which is this one. So in order for you to find the del 5, you can compute this one. Okay, so don't you might asking why just not direct compute my del E over del W35 directly by express this one. Of course, if you want to do it from scratch, then you can also do it from scratch like this one, and then once you find this one, then you can compute from this expression, you can compute the value. You can start execute this one to get value that can represent your del E over del W35. But I just added a few notation, which is E5 and delta 5, and then I define that my delta 5 is equal to to del E over del net, and actually this one is come from here, and then after do some replacement and manipulation, I find out actually my updater W35, my updater of W35 there is equal to this one, which is the same things, and then I'm using this notation delta 5. Is not using this one anymore, but of course I just want to show you that this one is the similar thing as what we express over here. Okay, it's nothing, but why I make you suffer by introducing another variables or another notation here, which is delta 5 and E5, because later we will use that to generalize all the equation. That is the purpose. Okay, just remember that is the purpose of generalize all the things there. Later you will see that, we will see that later. Okay, so of course if you talk about all parameter involved in output layer, in order for you to find the updater of every parameters there, doesn't matter is it W or B, then you can repeat the same process like this one, and then that is what you get in general. Or in general we can express in that way, means that to find the updater of W35 you need to multiply between your alpha, delta 5 and O3. To find the W45 updater, then you need to multiply between the alpha times delta 5 O4, and then for the bias B5, the updater, you need to multiply between the alpha times the delta. Actually it should be time 1, but I just remove it. Okay, time 1, remember this one, just imagine that. Okay, now you can see the patterns there. Okay, to find del E over del B5, you must multiply alpha, you must multiply with delta 5, and then multiply with 1. Okay, and then to find del E over del W35, you need to multiply your I'm sorry, this one let me repeat again how to I try to okay, let me remove the handwriting first. Okay, you can see that of course every updater you need to multiply with alpha. That is of course alpha need to multiply with your gradient here to find the updater. But of course this one is just simply if you set into alpha with certain value, then you just multiply with the gradient. Now for each and every gradient here, for example gradient happen here, gradient here, so del E over del B5, how to find that? Because again this one can't is the one that you need to multiply with alpha, so you can get the updater of B5. So how to find that here at this one? So then you just simply multiply between the delta 5, okay, multiply with 1 to find, okay, so that's how you get this one should be multiplied with 1. So to find the del E over del W35, you need to take this del 5 multiply with O3. So that's why here you can see that to find W35, delta 5 multiply with O3. Okay, delta 5 multiply with this one, you get this one. Delta 5 multiply with this one, you get this one. And then again to find del E over del W45, delta 5 multiply with O4, then you get this one. So you can see that that is the pattern. So that's why I introduced to you with this delta 5, which is a local gradient. Okay, it's a local gradient inside this node. Local gradient of node 5. Okay, it's beneficial for you to generalize everything. It means that at the node 5 to find delta E over delta B5, then you just multiply your this one with this one. To find this one, multiply this one with this one. To know this one, multiply this one with this one. So then you get everything's there.